Good afternoon. My name is Mehdi Benis. My talk today will be about extreme URLLC for ultra reliable low latency communication. All right. So first, let us start with URLLC and some facts. What we know today is that URLLC is in fact is the statistics of extreme and rare events. Where the goal is to characterize and tame the tail distribution of a probability distribution function. This could be your latency, it could be throughput, or any other key performance indicator. And for this, from a theoretical perspective, we looked at it using several mathematical tools such as extreme value theory, value at risk, and others. And typically the key performance indicators here are packet error rate, system failure rate, survival times, and others. Now, from a TraceGPP perspective, of course, where the goal is pretty much the same, but the focus here is on using system-level simulations to gain insight on the results. Okay, so here TraceGPP has done a great job in terms of coming up with several enablers, such as changing the numerology, and then of course coming up with grant-free transmission, especially in the uplink, and a number of techniques such as of course time, frequency, and special diversity techniques. But again, the focus here has been on communication reliability, because I will come back to it later. Just a few takeaways here, of course. So 5G URLLC, I mean, the gains behind, ultra low latency and high reliability usually come at the expense of sacrificing spectral efficiency, right? I mean, this is, in order to ensure reliability, well, you retransmit your packet a number of times, or you need to basically allocate more transmission points, as in multi-connectivity. So you need to sacrifice spectral efficiency, and of course energy. This goes hand in hand, and sometimes you need to over provision resources in terms of resource blocks or high transmit power. The assumptions here has been so of course the focus has been on sparse deployment, and meaning not so dense. And pretty much the environment is controlled, right? These are not, say, uncontrolled environment where with harsh propagation and so on and so forth. Although that is, of course, now changing. And as you can see on the right, of course, that when 5G came, the breakdown between EMBB, URLLC, and MMTC was actually a zero-sum game. But now we see that that is changing, and the boundaries are being blurred. For instance, virtual reality application may require not only EMBB but also URLLC. Likewise, for robot, requires EMBB for vision, but also URLLC and even MMTC. Okay. Now, of course, in 5G URLLC, ensuring reliability when you have plenty of when you have no issue with the model is relatively easy. Now things become more difficult when we don't have access to models. This is precisely the current focus of statistical and predictive URLLC, because in fact this tail distribution is not given a priori, and it has to be learned typically based on samples. This could be your channel samples, this could be your latency samples, or other data distribution that you may have. So to solve this problem, typically this can be cast as a machine learning problem. So reliability has to come hand in hand with sample complexity, because now the reliability that you need to ensure is going to be a function of how many samples you have for learning the distribution. By learning, I mean here you need, of course, to train your distribution, which is a separate subject on its own. But yeah. So this brings in machine learning, of course, to the picture in terms of, is it data-driven approaches or model-driven or a hybrid, when you actually have some prior information here from your environment or even from the application. But typically the questions as seen here is how many samples you need to learn a model for a given target reliability, while being robust to, of course, the model phenomena, but also unmodel phenomena. And this is where, in fact, machine learning may be even more helpful. Okay. Now, as we know, machine learning is all about generalization. So this is also key here in the realm of URLLC. Also, control stability is key, especially when talking about cyber physical control systems, and I will come back to that later. So there are a lot of trade-offs to be studied. And still within the realm of cyber physical control systems, these are, of course, very important in beyond 5G and even towards 6G. When we talk about centralized control or collaborative control, human control collaboration. Here again, the same problem is, can you control an object or robot when you don't have access to a model, right? So, which means you need to do it from data. So again, this brings in the whole notion of sample complexity, robustness, control stability here are key measures going beyond communication reliability. Okay, and this brings in an important component of the co-design between communication control, which is part of this extreme URLLC vision. So in fact, what we have is we have two extremes that are emerging. On the one hand, you have the quest for taming the tail distribution and going for 9 nines and even more. And on the other hand, we also should start maybe asking the question: can we relax some of this communication requirement? Because now if you talk to KUKA or other robotics companies, in fact, they will tell you that what they care about is in fact system stability or the failure of their system when three packets, consecutive packets are lost, or five. Okay, they don't care about one packet with a given communication reliability. Okay, so packet error rate for them is meaningless. The focus is whether I receive reliably three packets of five. Okay, so this actually allows us to now to revisit URLLC from a different standpoint, meaning can we relax this reliability measure by instead focusing on control stability or control safety. Okay, so this brings us to the vision of extreme URLLC, which is actually broken down into three aspects. So you have the first aspect, which is on the bottom part here, called URLLC. I mean, predictive URLLC, you can say, but also includes, of course, TSN and other efforts in that regard. Then we have on the left what I call non-RF. This is actually an important aspect where we need to use different modalities in order to predict more reliably and maybe achieve those 9 nines. Okay, because sometimes your data carries no statistical relevance, so one needs to now go for different modalities, and among them here, of course, is vision. So we could use RGB depth cameras, LiDARs, thermal sensing cameras. And the question, of course, here is how do you fuse these modalities? Because sometimes having more modalities is not really the way to go about it, but this is a fundamental problem on its own. And then you have on the top right, you have this COCOCO, which is communication control co-design, which I just stressed. This one comes with its own requirements of stability, controllability, observability, of robustness. This is, in other words, when control theory meets machine learning, but also communication. So there is a lot of interesting aspects in this. And finally, just some examples of recent works. On the one here on the top right, top left, this is the communication efficient massive UAV path control, mixing federated learning and in-field game theory. On the right hand side, we have been working on the problem of predictive control communication co-design using machine learning, in this case Gaussian process regression. And then finally, just some very interesting works working on looking at nonlinear control and remote monitoring over wireless. Thank you very much again for inviting me, and I wish you a very fruitful workshop. Thank you.